Bismillahirrahmanirrahim. Today's video will be discussing example 5.3, and for this a student has requested. So let's see. We start with the zero gate voltage, but before that, this is the diagram, or the structural diagram, you can say. And we have the body, substrate, and then this source and drain terminals, and we have gate terminals. The details I have explained in another video, so you can watch that. We're starting with the zero gate voltage. So if there is zero gate voltage, no channel will be formed. No current will flow from the drain to source, even when voltage VDS is applied. So even though we applied a VDS voltage, no current will flow because there is no path. Now this I'm describing some of the background of the theoretical background. If you have already understood, then you can skip and go to the problem straight away. Okay, for my ease, I've just turned this and then related with the equivalent diagram for the MOSFET. So you can see gate is here, and then we have drain at the top and source at the bottom. This also, if we relate with the transistor, it will become easier to visualize. The transistor, emitter, base, and collector. And first of all, let's establish the requirement for conduction. So as we know, in case of a transistor, we need to have 0.7 volt for the transistor to conduct. Similarly, in case of a MOSFET, we need to have a voltage. This voltage is called threshold voltage, or VT or VTH. So this voltage is required, and it depends on the type of transistor, how much is the voltage. And for conduction, the gate to source voltage, GS, has to be greater than or equal to VT. That is the condition. A term which you will come across is VOB, VOV. This is called the override voltage. And this may be very confusing. At least I got confused several times. So what I have done is I have related with a picture so I can remember it easily. Now, excess of VG over VT, that means VG minus VT, is termed as overdrive voltage. Overdrive voltage is VOV, and you can also write VG minus VT is equal to VOV. Now, if we relate with this, this is the speed limit, and we can compare it, or we call it VT, the threshold voltage, or even some books call it VTH, and some books call it VTN if it is an NMOS transistor. Now, if you are speeding at 150 kilometers, or if you are driving at 150 kilometers, then what will be the overspeed? Overspeed is actual speed minus the limit, that was 150 minus 120 is equal to the overspeed. Same logic can be applied here. The overdrive voltage, which we call VOV, is actually VGS, the driving force GS here, minus the limit or the threshold. So you can just correlate if you want. Now, another diagram which we'll be using throughout, very important diagram, is if we monitor, or if we draw a line from source to drain, and then at the input side we have the voltage, and let's take the voltage VGS. VGS can be divided into two parts, VT and VOV. see from this diagram here, VGS, gate to source volt, is equal to VT plus VOV. So we divide it into two parts, VGS. Now, one important point is that VT is fixed, given in the question or the manufacturer, and so will VOV be fixed for a particular GS. So these two spaces are fixed. And this can be written several ways. You can, this was the original equation. From here you can write VG minus VT is equal to VOV, or VGS minus VOV is equal to VT. Now, on the right hand side, this was the left hand side. On the right hand side, we'll write the DG and DS voltages. That is gate to drain and drain to source voltages. As in case of a transistor, we know that sum of the three voltages equal to 0. So from here also we can say that VGS is actually sum of VDG plus VDS. So VGS is actually sum of VDG and VDS. Now here there could be at least 4 variations here. And the first one is that this value of VDS is very, very small as compared to VOV. That means VDG is large and VDS is very small. So this is one case. The other case is that we have increased VDS, but it is still less than VOV. So VDS is less than VOV. Here it was less than VOV. And so it is, the VDG is still greater than VDS. The third case could be that they are equal, both, or the VDS is equal to VOV. And the fourth case would be that VDS is now greater and it is greater than VOV. So we'll consider all these 4 cases. Now let's start and let's create a channel first of all. So if we apply a voltage at the gate and keep the other, the source and the drain grounded, then there will be channel formed. Now if you compare, when there was a 0 voltage, there was no channel formed. Now there is a channel formed, but it is just like we have made a road, but no traffic allowed as yet. Same here, the channel is formed, but no current flows because there is no driving force, source or drain. Next comes to our first condition, that VDG is less than VOV. VDS is much less than VOV. That means we have just applied a very small voltage here. VDS voltage is very small. So what will happen is that the current will start flowing through the channel. Current ID to flow through the induced channel. And for a small VDS, the channel behaves as a linear resistance. So VDS is very small. Now if you see this diagram, the characteristic graph, this is VDS and this is voltage. This is the ID current, and these are the characteristics curves. Now this line is the locus point where we change from triode region to saturation region. There are 2 regions, and this particular point here represents the VOV, the overdrive voltage. Overdrive voltage. Now let's say the overdrive voltage is 4, somewhere here actually. Then when we are saying that VDS is less than VOB, that means it is somewhere here. And so this is the area we are operating, and the lines are linear, straight line, and this is what it means, that there is a linear resistance, and we are operating in triode region. So the MOSFET is the linear region or triode region or ohmic region. Now come to the second case. Now VDS is less than VOB, but more than what we had earlier. That means VDS is now has come close to, or gone up, but it is still less than VOB. VDS is less than VOB. That means with reference to this diagram, we were here, and now we are maybe somewhere 3.5. So we are still in the linear region or the ohmic region or the triode region. Okay, now before we proceed further, we have to build a concept of channel depth. You can see here the channel is not straight. It has more depth here and less depth here, and this is a taper shape. So for this condition, we are considering the channel depth depends on the effective value of VGS. So this will depend on the effective value of VGS applied through the channel. Now, what is the voltage between the source and drain and decreases from VGS 0 to VGS minus VDS? Let's see another diagram, this one. This is the effective value at this end, that is VGS minus 0, so VGS minus 0. What is the effective value on the drain side? VGS minus VDS, VGS minus VDS. Now, since VDS is obviously has some value more than 0, and therefore VGS minus VDS will be comparatively less than what we had here. That is why it is tapered. And now we can relate actually that VGS, we can say it is proportional to VGS minus VT, because VT is constant, and constant subtracted from a fixed value does not affect. So we can say that VG can be written as proportional to VGS minus VT, and VGS minus VT we know is actually VOV. So we can say it is proportional to VOV. So this is on the left hand side. We are on the left hand side of this diagram. Now similarly on the right hand side for VGS we put VGS minus VT. So we can say that the right hand side is proportionate to VOV minus VDS. And that is how our diagram we write like this, that the left hand. So now we can relate the channel depth with VOB. Left hand side or the source side is proportion to VOV, and the right hand side is proportion to VOV minus VDS. Okay, now we consider, we come back to our earlier discussion that VDS is less than VOV. So it is here now. Earlier it was here, very less. Now it is here. It is, and as we had been discussing, this line is actually the voltage drop across the channel from left to right or from source to drain. So this is the voltage drop. Then this much voltage is available for the channel. So we have highlighted it with the yellow color. So this is the effective voltage that will derive the depth of the channel. So the channel depth is just similar to this, proportionate to this. And we are still in the triode region because this is the line VDS is less than VOB. So this is DS line, and let's say this is the VOB point. So if we are at here, then VDS will be somewhere here, less than that. That means we are in the triode region. And so for the triode region, the conditions are that the VDS has to be less than equal to VOB. Or on the other hand side, we can also take the upper part, that is VGD has to be greater than VT or VTP. So these were the first two conditions. And now we come to the last two conditions. Now it is saying that VDS is greater than equal to VOB. We'll divide it into two parts. First of all, we consider VDS to be equal to VOB. So now see this diagram, VDS has now become equal to VOB, has been increased. And what will happen to the depth, channel depth? We can straight away from here see that this is the effective part. Now this is the voltage drop. So the effective part, let's mark it with the yellow. Okay, but before going into that, we can also do the mathematical calculation for this one. We know that VDS is equal to VOB from here, and VGD is equal to VT, VGD is equal to VT. So from the upper one, we can write that VOB minus VDS is equal to 0. That means this term will become 0. That means this depth will become 0. So the channel depth at the drain end reduces to 0. So this will become our channel depth diagram. And as I was saying, that we can also conclude from the available voltage here, mark it yellow, so it is the same shape, so proportional to the available voltage. So this was the third condition. Now here you can see one more point, yes, very important point. This, the end where it has become very sharp is called the pinch off point, or it has pinched off. Pinched off does not mean that it will stop current flowing, but what it means is it will allow very thin or very small current flowing, constant current flowing through the channel. And the MOSFET is said to have entered the saturation region. Now we are here. We are exactly at this point, that the V is equal to VDS. So this is the VDS and V same. Therefore, we can say that we are in this region, saturation region. The next point is that we are taking now the last step. VDS is greater than VOB. So VDS has increased further and it has become greater than VOB. Now you can see the voltage drop has gone up. So this much is the drop. So what is available for the channel is only this much of the voltage. So the channel will take this shape, or channel depth will be of this shape as shown in yellow. So the depth will be this shape. Now if you compare with the earlier diagrams, earlier the end point was here. Now it has gone towards the left or toward the source side. That means the length has reduced. The length of the channel was L, it has now reduced to L minus delta L. Now this phenomena has another name. It's called the channel length modulation. So when channel length is reduced with the increase in VDS, then it is called channel length modulation. And we'll be using this in the example that we solved. And what about the region? We are still in the saturation region, because now VDS is somewhere here, much greater than VOV. So the MOSFET is in saturation region. So what is the condition now for saturation? That VDF has to be greater than equal to VOV, or VGD has to be less than equal to VT. So this is the condition for the saturation. So these were the 4 conditions we can summarize, and the region of operation can be found from this table, the triode region and the saturation region. So we'll use this for solving problem. One more important thing, once we have decided whether we are in triode region or in saturation region, then we can use the current equation. So for saturation, we can use this equation. This is simplified one. And for triode region, we can use the equation on the left. Okay, now we can start our question. Okay, now let's solve the example. Let's discuss the example solved in the book. This is the circuit diagram, and the parameters are given here. So the first thing I prefer to do is replace these voltages with the proper batteries, so it becomes easy for me to write KVL equations. Then VD is given to be 0.5, so enter that. Current is 0.4 milliampere. And now we'll write the KVL equation for this loop. So minus VDD plus IDRD plus VD equals 0. And from here we can calculate RD. So this becomes the formula for RD. And all values are known, so we'll just plug in the values. 2.5 and then VD 0.5 and 0.4 milliampere. So RD becomes 5K. So this is first part, one part. We have to find RD and RS resistors. Now, how to find RS? First of all, let's see write the KVL where RS is present. So we'll write KVL in this loop. So plus VGS plus IDRS and minus VSS equals 0. And so RS is VSS minus VGS over ID. Now VSS we know, given ID we know, but we don't know VGS. So what is VGS, or how much is VGS? Now we know this formula for VGS, that VGS is equal to threshold voltage plus the overdrive voltage. You've seen this earlier also. VT, or the threshold voltage, is given in the question to be 0.7. VOV we have to find VGS. How can we find VOV? We have seen earlier that the transistor current equations in the triode region and also in the saturation region both have VOV in them. And so we have to first of all decide whether the transistor is operating in triode region or in saturation region, and then we can use this equation to find VOV. Now in the book, he has just commented that we know that since VD is 0.5, is greater than VG, which is actually ground 0, the NMOS transistor is operating in saturation mode. Now, this, at least I'm not convinced how to conclude this. There might be some other formulas, but I'll follow what we have just learned. So we had this for these conditions for the transistor to be in the triode region or in the saturation region. And this can be interpreted as VD greater than VG, VD greater than BG. Then we move T to the right hand side, and then we just reverse them. So VG minus VD is less than equal to 0. Now VG minus VD is actually VGD. VG minus VD is VGD. So VGD is less than 0. And now in these two conditions, where does it fit? Let's first of all try this. Here VGD has to be greater than some value VT. In our case, it is less than. Therefore, obviously, the transistor is not in the triode region, so it is in the saturation region. So we'll use the formula for the current from the saturation region table. And these are the values given. The only thing we have to keep in mind that this one voltage, mu and COX has 1000 microampere. Now our current is in milliampere. So we have to convert this into microampere first of all. So it will become 400 microampere. And now we have all the parameters for the equation. So we just put the values, not equation 1, equation 2. You can see W is 32 micrometer and length is 1 micrometer and all others. So from here we find VOB. VOB is 0.5 volt. Now that we know VOB, we can find VGS. VGS, this formula, we have already known VT or given 0.7. VOB is 5.5. So VGS is 1.2. And now going back to the formula for RS, this was the formula for RS. Here we'll now plug in all the values. This is given already, this is given, this one we calculated 1.2. So RS will be 3.25 kilo ohm. I hope you have been able to follow this. Please let me know through your comments. Thank you.